Hi, my name is Mohammad Amin Nabian. I'm a senior software engineer at NVIDIA, and today I will present NVIDIA SimNet, an AI-accelerated multi-physics simulation framework. So I will start the presentation with a brief introduction to SimNet, followed by a general overview on the neural network solvers. Next, I will show some sample SimNet use cases, including solving complex multi-physics systems, solving problems with complex STL geometries, efficient design optimization, and design space exploration, and also solving inverse problems. Finally, I will present some performance upgrade results for multi-GPU and multi-node training, and also learning rate scaling. Simulations are pervasive in every domain of science and engineering, and these simulations become computationally expensive as more geometry details are included, and as model size, the complexity of the physics, or the number of design evaluations increases. Deep learning techniques are usually used in form of a traditional data-driven neural network to overcome some of these challenges. However, generating data is expensive and time-consuming, and also models may not obey the governing laws. They might involve extrapolation and generalization errors, and they may provide unreliable results. SimNet aims to address the current computational challenges with the traditional and data-driven solvers. SimNet is an AI-accelerated multi-physics simulation framework, and compared to the traditional numerical solvers, SimNet addresses a wide range of use cases that includes coupled forward simulations without any training data, and also inverse and data assimilation problems. SimNet also offers fast turnaround time by enabling parameterized system representation that solves for multiple configurations in a single training. As an example, as it's shown in this figure, SimNet enables design optimization of an FPGA heatsink through a single training with no training data. SimNet is capable of addressing various areas in science and engineering, as shown in this figure. These include inverse and data assimilation problems, improved physics and predictions, real-time simulations with applications in digital twins, and also design space exploration and design optimization. So an overview of the SimNet structure is shown in this figure. The geometry module, the PDE module, and the data are used to fully specify the physical system. The user also specifies the network architecture, the optimizer, and also the learning rate schedule. SimNet then creates the neural network solver, forms the loss function, and unrolls the graph efficiently to compute the gradients. The SimNet solver then starts the training or inference procedure using TensorFlow's built-in functions on a single or a cluster of GPUs, and then the outputs are saved in form of a CSV or VTK files, and can be visualized using TensorBoard or ParaView. So SimNet currently includes two main geometry modules, namely the constructive solid geometry or CSG module, and the tessellated geometry or TG module. With the CSG module, constructive geometry primitives can be easily defined and Boolean operations can be performed. As an example, this figure shows a sample of the NV switch heatsink geometry that is created by our CSG module. This will allow creation and parameterization of a wide range of geometries. Also, the TG module in SimNet imports STL files, OBJ files, and also other forms of the tessellated geometries. And one thing to note is that the geometries in SimNet are all represented by point cloud, and we don't use any mesh in SimNet. The PDE module in SimNet contains a variety of common differential equations that includes the Navier-Stokes equations, diffusion and advection diffusion equations, linear elasticity equations, wave equations, and the equations for electromagnetics. The PDE module in SimNet also includes the implementation of a zero-equation turbulence model, and implementation of a two-equation turbulence model is currently in progress. In addition to the standard fully connected neural network, SimNet also offers a number of more advanced architectures, including but not limited to Fourier feature network, modified Fourier feature network, and sirens. So SimNet currently offers the Adam optimizer and the BFGS optimizer. It also offers gradient aggregation that enables large batch training even on a single or limited number of GPUs. And it also offers other optimizer tools for loss weighting, including uncertainty loss weighting and global or local learning rate annealing. So in the next part, I will briefly talk about the neural network solver architecture and methodology. So briefly, a neural network solver approximates the solution to a given PDE and a set of boundary and initial conditions using a feed-forward, fully connected neural network. The model is trained by constructing a loss function for how well the neural network is satisfying the PDE and the constraints. And if the network is able to minimize this loss, then in effect, it will solve the given PDE. A sample structure of the neural network solver is shown in this figure. The input to the network are the spatial coordinates of the point cloud, realizations of time if we are solving a transient problem, and also realizations from the parametric space if we are solving a parameterized problem. And then the inputs are mapped to the quantities of interest through a fully connected network with nonlinear activations. And to train this network, a loss function is considered, which consists of derivatives of the output with respect to the inputs, which is compared using the automatic differentiation, and also the initial and boundary condition information. So let's consider the following general form of the PDE, where n here is a general differential operator and x is the set of independent variables defined over the bounded domain D, and also u here is the solution to the PDE. C also denotes the set of constraints that may consist of differential, linear, or nonlinear terms, and usually covers the boundary and initial conditions. So we want to approximate the solution U by a neural network UNet that in its most simple form takes this form, where again X is the input, phi i's are representing the hidden layers, and phi e is an input encoding layer. In a standard fully connected network, phi e is just an identity function. But in the Fourier feature networks, it includes Fourier basis encodings. And then in order to train this neural network, we construct a loss function that analyzes over the divergence of the approximate solution and such that the constraints are encoded as penalty terms. And to this end, we define these following residuals here by using UNet as the approximate solution to the given PDE. And then with that, so here R sub n represents the PDE residual and R sub c represents the constraint residuals. And then with that, we can formulate our loss function in this form, where here P represents the norm, lambda sub n and lambda sub c are weight functions that control the loss interplay between different terms. And later in this presentation, we will see that using the signed distance function or SDF for loss weighting can greatly help with the training convergence and accuracy for neural network solvers. So in the next few slides, I will show some sample use cases in SimNet. The first one is conjugate heat transfer. In this example, we show that SimNet is able to accurately solve multi-physics problems involving high Reynolds number flows. The geometry of the FPGA heatsink is shown here. This geometry is challenging to solve because the spacing of the fins is really close, and that causes some sharp gradients in the solution, which are difficult to learn for a neural network solver. Using a zero equation turbulence model, we solve this conjugate heat transfer problem to simulate the flow over the heatsink, and the Reynolds number for this problem is around 13,000. And since we are dealing with the incompressible flow, there is a one-way coupling between the heat and the flow equations, and therefore we train two different neural networks, one for the flow and the other one for the heat. And using SimNet, we simulate this conjugate heat transfer problem. The results are shown here with a comparison with the OpenFOAM results. And as you can see, SimNet and OpenFOAM results are in good agreement. So we have also solved this conjugate heat transfer problem with Fourier feature network and modified Fourier feature networks, as well as Seidens. And the results are shown here for the loss curves. In this example, Fourier network and modified Fourier networks are showing better convergence compared to the other architectures. This figure also includes the flow convergence results for a Fourier feature model with no sign distance function weighting, and also another model trained with a standard fully connected network. And it is evident that both of these models fail to provide a reasonable convergence. And this highlights the importance of using Spf Loss Weighting and more advanced architectures. In this slide, I will talk more about two techniques that we are using to improve the convergence and accuracy of neural network solvers. The first one is Spf Loss Weighting. And in general, we have found that it is beneficial to weight losses lower on sharp gradients or discontinuities around in the domain. If the geometry has sharp corners, this often results in sharp gradients in the solution of the PDE, and weighting by the SPF tends to remove these effects of sharp local gradients and often results in a convergence speedup as well as better accuracy in some cases. The second important technique for improving convergence is the integral continuity planes. For some problems that involve channel flow, we found that in addition to solving the Navier-Stokes equations in the differential form, specifying the volumetric flow rate through some randomly placed planes in the domain can help in satisfying the continuity equation better and faster, and it can help with improving the accuracy further. The next example is flow in an aneurysm. In this example, we want to demonstrate the ability of SimNet in handling the STL geometries. Using the SimNet tessellated geometry module, we simulate the flow inside the patient-specific geometry of an aneurysm, which is shown in this figure. The SimNet results for the distribution of the velocity magnitude and also the pressure developed inside the aneurysm are also shown in this figure. There is also a comparison with the OpenFOAM results, and as you can see, again, there is a good agreement between the SimNet and OpenFOAM results. When solving the forward CFT problems with non-trivial geometries like this geometry, one of the key challenges is getting the flow to develop inside this aneurysm stack correctly in this example. And the streamlines here show that SimNet is capable of detecting these streamlines very correctly in this aneurysm stack. The final example is a design optimization example for industrial systems. In this example, we show that SimNet can solve several simultaneous design configurations in a multi-physics design space exploration problem much more efficiently than traditional solvers. This is possible because unlike a traditional solver, a neural network solver trains with multiple design parameters in a single training run. And once the training is complete, several geometry or physical parameter combinations can be evaluated using inference as a post-processing step without solving the forward problem again. And this enables more efficient design optimization and design space exploration tasks for complex systems. Here we train a conjugate heat transfer problem over the NVIDIA's NV switch heatsink, whose fin geometries are variable. We have nine geometry variables in total. And following the training, we perform a design optimization to find the most optimal fin configuration. In the heatsink design, usually the objective is to minimize the peak temperature that can be reached at the source chip while satisfying the maximum pressure drop constraint. So the fluid and heat neural networks in this example consist of 12 variables in total, 9 for the fin geometry variables and 3 for the spatial variables. And then using SimNet, we train 2 models, one for flow, one for heat, to compute the pressure drop and peak temperature corresponding to various parameter combinations. And the optimized design is the one that minimizes the peak temperature while satisfying the pressure drop constraint. And this figure here shows the streamlines and the temperature profile for the most optimal NV switch geometry that is obtained using SimNet. So by parameterizing this geometry, SimNet significantly accelerates design optimization when compared to the traditional solvers, which are usually limited to single geometry simulations. And the total compute time required by OpenFOAM, a commercial solver, and SimNet are reported in this table. And it is evident that SimNet can solve this design optimization problem much faster compared to the other traditional solvers. I have one more example, which is the inverse problems. Here in this slide, we show the ability of SimNet in solving data assimilation and inverse problems on a transient flow past the 2D cylinder. Given the data consisting of a scattered concentration of a passive scalar in the flow domain at different times, the task is to infer the flow velocity and pressure fields, as well as the entire concentration field of the passive scalar. So we construct a model with a hybrid data and physics-driven loss function. And specifically, we require the neural network prediction of the passive scalar to fit to the measurements, and also to satisfy the governing laws of the system, that are the Navier-Stokes equations and the advection diffusion equations. And here the quantities of interest are also modeled as trainable variables and are inferred by minimizing the hybrid loss function. The figure here shows a comparison between the SimNet results and the OpenFOAM results for a snapshot of the flow velocity, pressure, and passive scalar concentration fields. And once again, the SimNet and OpenFOAM results are in good agreement. And in the last part of my presentation, I will talk about some performance upgrades briefly. So SimNet supports multi-GPU and multi-node scaling to enable large batch sizes, while time per iteration remains nearly constant, as shown in this figure. Therefore, the total time to convergence can be reduced by scaling the learning rate with the number of GPUs. And the figure here on the right shows the results for large batch training acceleration on A100 GPUs using learning rate scaling. To achieve a certain loss value, it takes about 82K iterations on a single GPU, while it takes only about 18K iterations on 8 GPUs. Also, SimNet supports kernel fusion using XLA that, based on our experiments, can accelerate a single training iteration by a factor of 3.3. Also, SimNet supports the TensorFlow 32 math mode available on NVIDIA A100 GPUs. And again, based on our experiments, compared to the FP32 mode, TF32 provides 1.6x speed up on A100 GPUs and 3.1x speed up over FP32 on V100 GPUs. SimNet is available to download free of charge from our website, developer.nvidia.com/SimNet. And also for more information about SimNet, please refer to our paper. The link is shown here. That concludes my presentation for today. Please feel free to contact me via email or LinkedIn if you have any questions. Thank you.